Imagine building something today, not for 30 years, not for 100, but for 2,000 years. Now imagine that structure surviving storms, saltwater, earthquakes, invasions, neglect, empire collapse, and time itself. While many of our modern concrete structures begin cracking, corroding, and failing in just a few decades. That sounds absolutely impossible. And yet, all across the Mediterranean, the proof is still there. Roman harbors, seawalls, aqueducts, vaults, domes, breakwaters, still standing. And that raises a deeply uncomfortable question. How did an ancient civilization without computers, steel rebar, or modern chemistry create concrete that often outlived ours? Because this isn't just a cool historical curiosity. This is about what we chose to forget. And if Roman concrete really was more durable in some of the harshest environments on Earth, then this isn't just a story about the past. It's a story about what modern civilization may have abandoned. And once you understand why it worked, the real mystery isn't how the Romans made it. The real mystery is, why did we stop? Concrete is everywhere. It's under your feet, around your cities, inside your roads, bridges, apartment towers, dams, tunnels, sidewalks, parking garages, and sea defenses. And yet modern concrete has a dirty little secret. It often doesn't age well. A bridge deck can begin deteriorating in a few decades. Parking structures need constant repair. Marine concrete is especially vulnerable. Saltwater, freeze-thaw cycles, corrosion, chemical attack, and structural fatigue slowly eat away at what we assumed was permanent. Modern concrete is strong, but very often it is not immortal. Roman concrete, on the other hand, was never supposed to impress us 2,000 years later. It was just supposed to work, and somehow it worked too well. That's what makes this story so fascinating, because the Romans were not chasing futuristic materials science. They were solving practical problems. How do you build a harbor that can survive the sea? How do you pour massive walls that don't collapse? How do you build an empire-scale infrastructure system that lasts? And in answering those questions, they may have stumbled into something modern. Engineering is only now fully appreciating. The story begins with a powder. Actually, several powders. Roman concrete, known in Latin as opus caementicium, was not exactly the same thing as the smooth grey concrete we picture today. Think of modern concrete like a highly standardized industrial recipe. Roman concrete was more like a rugged, mineral-rich, field-tested formula designed around local materials and long-term resilience. At its core, Roman concrete was made by mixing lime, volcanic ash, and rock fragments. That volcanic ash is the key, especially ash from places around the Bay of Naples, where volcanic deposits were rich in a material the Romans prized, pozzolana. Imagine you're making stone, but instead of carving it from a mountain, you're growing it into place. That's basically what Roman builders learned to do. They discovered that when lime reacts with certain volcanic materials and water, something remarkable happens. The mixture doesn't just harden like mud drying in the sun. It begins a chemical transformation. It starts creating new mineral bonds. In other words, Roman concrete wasn't just drying, it was becoming stone. And this is where things get interesting, because modern concrete also hardens through chemistry. But Roman concrete often behaved differently, especially over long periods and especially in seawater. That difference may explain why some Roman marine structures survived where many modern ones struggle. To understand why Roman concrete worked so well, picture two very different philosophies of building. Modern concrete is optimized for speed, consistency, and compressive strength. You want it pourable, predictable, scalable, and compatible with steel reinforcement. That makes perfect sense in a world of highways, towers, schedules, budgets, and mass production. Roman concrete was optimized for something else: endurance. It didn't care if a harbor wall cured quickly enough to satisfy a quarterly deadline. It cared whether it could take punishment for centuries. And the secret lies inside the material itself. Modern Portland cement concrete relies heavily on highly processed clinker, a product made by heating limestone and other ingredients to extremely high temperatures. This creates a binder that hardens efficiently and powerfully. But Roman concrete often used a different chemistry. Instead of depending mainly on that kind of high-energy industrial binder, it relied on lime and volcanic ash reacting together in ways that formed durable crystalline structures over time. Think of it like this. Modern concrete often behaves like a rigid, manufactured composite. Roman concrete behaved more like a living geological material. Not alive, of course, but active. Because in certain conditions, especially in marine environments, seawater didn't just attack Roman concrete. In some cases, it actually helped transform it. That sounds backwards, because water is usually the enemy of construction. But in Roman marine concrete, seawater appears to have triggered slow mineral growth inside the structure. Tiny crystals formed and strengthened the internal matrix over time. Let that sink in. Some Roman concrete didn't just resist damage, it may have actually improved in the presence of the environment that should have destroyed it. That is an astonishing design advantage. And it's one of the reasons Roman harbour structures remain one of the most jaw-dropping engineering achievements of the ancient world. Now compare that to what often weakens modern concrete.
One of the biggest problems is steel corrosion. Modern reinforced concrete depends on steel bars inside the concrete to handle tension. That system is incredibly useful and often necessary. But it comes with a weakness. If water and salts penetrate the concrete and reach the steel can rust, and rust expands. That expansion acts like a slow-motion internal explosion. The steel swells, cracks the surrounding concrete, opens new pathways for moisture, and starts a destructive cycle from the inside out. So, modern concrete doesn't just fail because the concrete is weak. Sometimes it fails because the system itself has an internal vulnerability. Roman concrete, especially in many marine structures, often didn't rely on that same dependency. And because it was built massively, thickly, and with a deep respect for compression, mass, and material behavior, it often tolerated time better. That's an important point. The Romans weren't just using a different mix, they were using a different philosophy. They built thick walls, heavy forms, curves, arches, domes, and vaults, shapes that worked with gravity instead of constantly fighting it. And that one mindset shift changes everything. A flat beam under stress wants to bend, an arch wants to carry. A thin slab can crack under concentrated stress. A thick mass can absorb and distribute it. Roman engineering often paired resilient material with resilient geometry. That combination is devastatingly effective. The Pantheon is the obvious celebrity example, nearly 2,000 years old, still standing. The Pantheon is the obvious celebrity example, nearly 2,000 years old, still standing. Still crowned by the world's largest unreinforced concrete dome. That alone should make people stop and stare. But the real proof may be even more impressive in places most people never visit. Roman piers, breakwaters, harbour blocks. Sea-facing structures battered for centuries by waves and salt. Because seawater is ruthless, it exploits tiny weaknesses. If you want to test whether a material is durable, put it in the ocean and wait. The Romans did, and somehow, a lot of it survived. That is not normal, that is not lucky, that is a signal. And once you see that signal, the obvious question arrives. If Roman concrete was this effective, why did we stop using it? This is the part of the story that becomes less romantic and more revealing. Because civilizations don't always abandon better ideas because those ideas stopped working. Sometimes they abandon them because the world around them changed. And when Rome fell, a lot more collapsed than government. Trade networks fractured, industrial coordination vanished, specialized knowledge scattered. A material recipe is not just chemistry, it's also logistics. We stop building for centuries. We start building for cost curves, schedules, scale, and immediate utility. That's not stupidity, it's industrial logic. Modern concrete won because it could be made faster, more uniformly, and almost anywhere. Portland cement was revolutionary because it democratized concrete production. In a rapidly expanding modern world, that mattered enormously. So yes, in many ways, modern concrete was a triumph, but it came with a trade-off. We optimized for convenience and speed, and often accepted lower long-term resilience as the price. Once your entire civilization is built on materials that require constant maintenance, you don't just create buildings, you create a repair economy. You create recurring failure as a normal business model. And suddenly, lasting forever is no longer the baseline expectation. It becomes a miracle. And this is why Roman concrete matters right now. What if part of the future of sustainable construction isn't hidden in some sci-fi invention, but in an ancient material logic we dismissed as obsolete? That's not nostalgia. That's engineering humility. Because one of the strangest patterns in human history is this. We often assume newer means better until the old thing refuses to die. Maybe they were simply forced to respect physics, materials, and time more honestly than we often do. They didn't build for glossy renderings. They built for generations they would never meet. So the next time you see a crumbling seawall, remember this. Somewhere on the coast of the Mediterranean, pieces of ancient Rome are still sitting in the water, doing their job. Not because they were lucky, but because somebody learned how to build with time instead of against it. If you enjoy uncovering forgotten building knowledge, subscribe.